Okay, good afternoon. Welcome back. So it's a Friday. We'll be doing some statistics. Specific to our statistics students, you're likely taking the college statistics course through your community college. It likely has been remote, maybe the whole semester, but has gone remote recently with the COVID-19. So hopefully these are helpful. I know as well for some of you, you've gotten some time on Wisent. So talk to your coordinators if you think you want some tutoring, and we'll see if we can get you signed up on there. And you should be looking for instructions if you are signed up pretty soon if you haven't already figured it out. I know several of you have, so that's an option. Now, what we're going to talk about today, we're going to continue talking about probability. Okay. And in particular, we're going to talk about what's called the additive rule. Additive. Sorry about that. Spelling not my strongest suit. Okay. There's a couple of we'll get to it. We'll get to it in particular, but right now we're going to think about a spinner. So a spinner is a typical kind of theoretical space, although it also has practical purposes, where you have these wedges on a circular shape and a spinner that can move freely around them. So if you played some board games, you may have seen something like this or watched some game shows on television or something like this. Basically, you can think of the red arrow as something that can move, so it's attached to the middle and it gets spun. And it's equally likely in this case, well, it's equally likely in general of spinners to wind up pointing in any particular direction. So 360 degrees of the circle, like you could imagine, spinning it enough and then it eventually stops. In this particular case, I want to, as the setup for this spinner, though I hand drew it, we're going to say all wedges are the same size. So you could contrast that with a setup like this, where maybe this wedge and this wedge are double the size of the other four. That's not what we're going to be dealing with right here. We're saying that wedge 1, 2, 3, 4, 5, 6, 7, and 8 are all exactly the same size. Another way of saying that, from a probability standpoint, is the probability of getting a 1 is equal to the probability of getting a 2, and it's all of them are equal. Right? 3, 4, 5, 6, 7, and 8, they're all equal probabilities, all equally likely. So all the wedges are the same size. So we can ask the question right off the bat, like, what is the probability of getting a 3 on a single spin? So the spin of this pointer on the spinner, what is the probability that it winds up stopping on a 3? Well, if they're all equally sized and all equally likely, the likelihood of any particular number is 1/8. Okay, sit with that for a second. Hopefully it makes sense. There are 8 wedges. They are equally sized. They take up the entire spinner. You know, if you spin the pointer, it will land on the spinner, right? So we're not thinking we're in this abstract universe where kind of physical problems like maybe the spinner breaking and flying off or something, that isn't something we're considering here. We're saying it's going to successfully spin. It's going to be random, right? So we're not able, or at least we're not thinking in this abstract place that we could maybe aim the spinner and try to spin it with a certain strength so that it stops on a particular number. No, we're trying to use this spinner as a randomization. And so in the abstract sense, we're saying spin the pointer with no preference to any of these numbers in this case. What is the likelihood it lands on a 3? Well, they're all equally likely, so 1/8. They are all 1/8. All of them are 1/8. So you can check, of course, this is a probability space, right? Because the probability of 1 is 1/8, 2 is 1/8, 3 is 1/8, so on, so on, so on. So all 8 of them, probability sums to 1, which is what you need for a probability space. Okay. A different question. What is the probability on a single spin that the spinner lands on an even number? Well, 1/2. Right? This is equivalent to asking, well, let me get there. We can tell what the even numbers are, 2, 4, 6, and 8. They make up half the numbers, half the wedges. Similarly, the probability of landing on an odd is 1/2. Okay. What is the probability? This is going to introduce a new idea for our videos, at least, of this or word. Okay. This is a very precise mathematical probability word. In our case, you may use it freely in your everyday speech in particular ways that are similar to, but also contrast sometimes with the precision that we're going to need here. We're precisely saying it could be a 2 or a 4 or both. Right? It could be a 2, 4, or a 2 and a 4. It could be a 2, 6, and a 4, and an 8, right? Or allows for and. So we're going to get to and as well. But in probability sense, or is more flexible. Now in the spinner case, that's not a big issue, but we'll look at, in this case at least, it's not a big issue. We'll look at one where it may be a bigger issue. Hopefully, oops, sorry about that. Forgot to switch off the highlighter. Hopefully you recognize that the probability of that would also be 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8. It is asking actually the same question as the above, probability of even, because those are all of the evens, right? One thing that's important here is actually these are mutually exclusive outcomes. The event that the spinner lands on a 2 never happens at the same time as the event that it lands on a 4 or 6 or 8. They are what is called mutually exclusive outcomes. Let's ask another question. What is the probability of a 2 or 3 or 4? Sip of water. Well, because these are mutually exclusive, meaning they cannot happen at the same time, you can look at the spinner here. You can never land on a 2 and a 3. You're either on one or the other. We can add, because they are mutually exclusive, okay, the probability of getting a 2 or a 3 or a 4 is equal to the probability of a 2 plus a 3 plus a 4. I'm sorry, probability of a 2 plus the probability of a 3 plus a probability of a 4. Now, in the background here, we actually do have the additive rule, which we'll get to. And it helps us kind of delineate the idea of mutually exclusive or a different idea of independence, which comes into play here. Depending on your text and your instructor, they may call this the addition rule. I learned it as additive rule. Addition rule is fine as well. Let's take a look at another question. Probability 3 or odd. Note the difference between the left-hand question over here, find the probability of 2 or 3 or 4, and this question. Say it out loud. What is the difference between that question? Obviously, they're different questions, but what is the most meaningful difference here? The thing that really will impact the strategy for answering this question. Hopefully it becomes clear. 2 is not 3 or 4. They are mutually exclusive. But 3 is odd. Right? 3 is odd. And so we fall, if we wanted to do it in the same question and we said, oh, well, it's the probability of getting a 3 plus the probability of getting an odd, which we know is 1/8 for a 3 and 1/2 for an odd, so 5/8. It's actually not true here, right? The answer, I think, if you're looking at this correctly, is 4/8, 1/2, right? Well, let's think about why. Let's use the highlighter here on the spinner to highlight the outcomes, which are successes for this event, right? Well, a 1 is an outcome that is a success because it's odd. A 3 is an outcome that's a success because it's odd and it's 3. A 5 is an outcome that's a success. And a 7 is an outcome that's a success. And notice the 3. Oh, it's a success because it's 3, because we're asking about 3. And it's a success because it's odd. We're asking about odd. So maybe I could circle as well and say blue meaning odd, red meaning 3. Okay, so 3 got double circled. But it doesn't mean we want to double count it. It doesn't make the 3 any more likely to happen or the odd any more likely to happen, right? And so we have to be careful here. What's happening, if we add them, we are in fact double counting the likelihood of landing on a 3, but the likelihood didn't change. It's still 1/8. We're saying it's 1/8 to be on a 3, and the 3 is also 1/8 to be an odd, but it's the same 3, so we don't want to double count it. So what we need to do is subtract something, and that thing is going to be written like this. Minus the probability of getting a 3 and an odd. So that double counting that I'm talking about, it is accounted for and remedied with this subtractive term. And this is going to be the general additive rule here. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, where A and B are any events, any particular outcomes that we care about. So what we'll see here is 1/8 to get a 3, 4/8 to get an odd, and minus 1/8 to get a 3 and an odd. So it'll be 4/8, it'll be 1/2. Which brings us pretty quickly to wanting to confront and think about this term, the probability 3 and an odd, right? I said it was 1/8 and we're subtracting it. It's this 1/8 being subtracted. But how do we really know that, or what does it actually mean? Well, let's think about it, right? You spin the spinner. The word "and" here, again, very precise meaning. It means both events are happening. So on a single spin, what is the likelihood that both a 3 and an odd comes up? Well, 1/8. If it lands on 3, it is also an odd. We should contrast it then with, say, this question. The probability that we get a 4 and an odd. Well, 4 and odd are mutually exclusive outcomes because 4 is even. No odd numbers are 4. This is 0. Think for a moment. What are some other and probabilities, so dual probabilities, two events, that have likelihood 0? 4 and odd is 1. What are some others? One way to come up with them is visualize the spinner spinning. It stops somewhere, say on 7. 7 has qualities, right? 7 is less than 8, 7 is greater than 6, or greater than 4, or greater than 2. 7 is odd, but it also has things that it is not. 7 is not even. 7 is not less than 6. 7 is not greater than 7. 7 is not 2. If you're thinking about a joint probability here, P of, say, 7 and, whatever you put here, if it's something that can never happen, something that is at the same time, something that is mutually exclusive to 7, then you will have a probability of 0. So fill that in with whatever you like. I'll go with 7 and less than 5. All right. But there are many options that could go in that blank and work here. Let's reset for the last 10 minutes, and I will draw a different spinner. And this will give you a sense of, if you want to practice this at home after this video, draw yourself a different spinner. Establish the probabilities of any of the specific simple outcomes. So in the setup here, the probability of a 1 is 1/8. Probability of a 2 is 1/2. The probability of a 3 is 1/4. The probability of a 4 is 1/8. Is it a probability space with this setup? Well, yes it is, because 1/8 plus 1/2 is 5/8, plus 1/4 is 7/8, plus 1/8 is 1. So 1, 2, 3, or 4 will happen on any fair spin of the spinner. And again, remember, we are, for our purposes of learning this in a theoretical sense, we will get to the experimental, right, where we're actually testing, say, a spinner for fairness. Here we're saying this as a setup, the spinner is fair, meaning the red arrow as you spin it is equally likely to wind up in any position spinning around this spinner, right? And therefore, just the physical space taken up by the wedges defines the probabilities. We can set them. 1 is 1/8 of the spinner, 4 is also 1/8, 3 is 1/4, and 2 is half of it, the left half. So what is the probability of 1 or 3? Well, it's by our additive rule, it's the probability of 1 plus the probability of 3 minus the probability of 1 and 3. Now I took 1/8 and 1/4 just from the left-hand side, from the setup. We know the probability of 1 and the probability of 3. I established this equal sign and what comes after it by the additive rule, right? When I am trying to calculate the probability of one event or another event happening, either can be successful, but I don't want to double count the moments when both might be successful. So in this case, this minus probability of 1 and a 3. Now, that probability of 1 and a 3 can very frequently be 0, right? If the two events are mutually exclusive. And in this case, look at the board, can never get a 1 and a 3. They don't overlap. So in fact, they are mutually exclusive, and we get 3/8. 1/8 plus 2/8. Right? So a lot of probability tests a little bit of your fraction addition. Make sure you're comfortable getting to least common denominator and converting fractions, equivalent fractional forms, very important. 1/4, 2/8, 3/12, so on. Those are all equivalent fractions. Okay. Deep breath. The probability of 2 or an even. Think about the statement. It's an or probability statement. We want to consider whether these are mutually exclusive. No, they are not. 2 is an even number. Therefore, when we establish the additive rule, we should expect maybe that the subtraction term is non-zero. Let's see how that looks. I think we have a sensibility here. The probability of 2 or an even should be 5/8. Right? Because we're really able to translate that question to the probability of a 2 or a 4. Those are the evens. So it kind of looks like the probability of a 2 or a 2 or a 4. But 2 or 2 can be reduced. The probability of just a, oops, I think this undoes that. Yes, it does. Right, so that's a sophisticated and nuanced thing to be thinking about, but it's also really, really useful, right? Don't abandon your intuition here. Probability of a 2 or even, it's quite clearly going to be a 2 or a 4. Those are the possibilities here. So what does it look like in this technical standpoint? Well, the probability of a 2 is 1/2 from the setup. Oops, I messed this up just a touch here. That should be a plus from the additive rule right there, not an or. Probability of an even looks to be 5/8. And the probability of 2 and an even would be 1/2. Right, like what is the likelihood that both of those happen at the same time, 2 and even? Well, every time it lands on 2, both of those happen. So we subtract the probability of being a 2. It's a very difficult, this is a difficult term to be working with. So you're going to practice it a lot. You're going to think about it in sophisticated ways already, right now, and in the future. Probability of 2 and an even. Right? It has to do with conditional probabilities, and we talked about that last week, and we will link them at some point in the future in a technical way, but also in a conceptual way. Let's do one more. Let me think about what could be a good one to stop on. This is sometimes written as the probability of the outcome being greater than 2 or less than 4, x taking the role here of a random variable, the outcome of a spin being taking on a value greater than 2 or less than 4. Well, really sit and think about this. Look at the spinner. Think about the outcomes that satisfy each of the two conditions here. The outcomes that satisfy being greater than 2 are 3 and 4. The outcomes that satisfy less than 4 are 3, 2, and 1. So just by speaking our way through it in that way, I think what you might be sensing is that I listed all the possible outcomes, 1, 2, 3, and 4, but I listed one of them twice, the 3. And that's an issue that is tackled by the additive rule. So this should be the probability that the outcome is greater than 2 plus the probability that the outcome is less than 4 minus the probability that the outcome is greater than 2 and less than 4. The probability that the outcome is greater than 2 is 1/4 plus 1/8, the probability of a 3 or a 4. The probability that the outcome is less than 4 is 1/4 plus 1/2 plus 1/8, the likelihood of a 3, a 2, or a 1. Minus, and here's where it gets pretty nuanced, we need to establish what outcomes are we talking about where both of these things happen. The probability that x is greater than 2 and less than 4 only happens on the outcome x equal 3, which has likelihood 1/4. So let's do a little bit of fraction rewriting. They all have the same denominator 8, so they're all out of the same whole. So I will add 2 plus 1 plus 4 plus 2 plus 1 minus 2. That's 3, 7, 9, 10, minus 2, 8. 8 over 8 equal to 1. Exactly what we spoke into existence here when we first thought about the question. The probability that the outcome of the spinner is greater than 2 or less than 4. Greater than 2 happens on 3 or a 4. Less than 4 happens on a 3, a 2, or a 1. The only outcomes are 1, 2, 3, or 4. All of them are accounted for. The likelihood of this happening is exactly always, or 1, or 100% of the time. So it's a good question. Makes us think, makes us hopefully recognize the unique ability we might have to think about this intuitively, of speaking our way through it, then worrying about the technical side and making sure to verify here we do in fact get 1. We are in fact doing it correctly. These are not mutually exclusive outcomes. An outcome can be greater than 2 and less than 4, exactly when it's 3. Oops. So thanks for joining me. If you're watching in the future, hope it helps. Remember to ask questions in the comments if you'd like, or come by next week's stream and ask questions. And I look forward to